Now, the strange looking picture is just a summary of what we did yesterday. I didn't want to sit and take time and draw it in front of you. But meanwhile, what do I have here? We had that yesterday, when we were calculating the area under the rate graph, right end, you can see all these, was the sum of those rectangles was clearly smaller than the area under the rate graph, which was clearly smaller than the rectangles we were using for the overestimates. Now we want to put a little calculus in here. Now what am I going to do? I'm going to say the bigger n gets, the closer this estimate gets to the actual area under the rate graph. Well, the bigger n gets, the closer this estimate gets to the area under the rate graph. And what we want to do is do a calculus thing and ask ourselves what would happen if I try to take the limit of the right sum. Yep, camera is winning the whole day today. There. What I want to do is take the limit of the right sum. Now, remember, that was an estimate. A limit says, what is the estimates getting close to? Well, what the limit is getting close to is the exact area under the rate graph. If these were all estimates, and I'm asking what are the estimates getting close to, that should be the exact area. So when I take the limit, I get ta-da-ta-da, equals. It's very cool. Same thing over here. If I take the limit of all of our estimates of the area under the rate graph, I'm asking what do the estimates get close to? What they're getting close to is the exact area under the rate graph. That's exactly what we mean when we say the limit equals the area under the rate graph. Now, I don't know if you realize this or not, but what we just did is we defined the area under the rate graph. Right? It's really hard to define it without it. But anyways, we have this lovely picture that says the limit of the right sum was equal to the exact area under the rate graph is equal to the exact limit of the left rectangles. Now I'm going to erase something here and not change anything. What were equal to all those areas yesterday? For some reason I want this to be in brown. Yeah, that's it. We were looking at amounts of escaped air. Not that AOEA is a famous acronym or anything, but we knew that the right sum was estimating the amount of escaped air. We knew that the left sum was estimating the amount of escaped air. We know that the bigger n gets, the closer the right n, the estimate gets to the amount of escaped air that we want, and the bigger n gets, the closer left n gets to the amount of escaped air that we want. And by the same reasoning we did before, if I take the limit of the estimates, I should get the exact value. If I take the limit of the estimates, I should get the exact value. So we get the exact same result we got before, but we get one more conclusion. And this is, I'm just going to put my little conclusion down as, ta-da, ready? The amount of escaped air must be equal to the area under the rate graph. That seems very strange. If someone said, show that the amount of escaped air is equal to the area under the rate graph, you're like, I don't know how to do that. But they're both estimated perfectly by the limits of the right sums and the left sums, and it's impossible for these to be squeezing in on the amount of escaped air and squeezing in on the area under the rate graph and be actually squeezing in on two different numbers. So we get this lovely conclusion that the amount of escaped air is actually equal to the area under the rate graph. Now, let me take 1 second and just remark on the example that you guys did that was very similar. Assuming my camera will stay focused for just a second. Stay focused, all right. So you guys looked at something that looked like that. Yes, and you weren't calculating amount of escaped air, you were calculating distance traveled, but it was the same thing. The right sum estimates the area under the rate graph in exactly the same way it estimated the distance traveled. The left sum estimated the distance traveled the same way it estimated the area under the rate graph, and we're going to get the exact same conclusion, that the area under this rate graph the one you guys did, was equal to the distance traveled. Now, by the way, when the rate was constant, that was obvious. That's a really cool thing, but now it says, wait a minute. If the rate's doing lots of wiggling and it represents the velocity, it is absolutely true that the area under the rate graph is still the distance traveled. All right, that's step 2.